peering into the depths of space. Each new telescope brings with it the promise of unveiling previously unseen wonders of the cosmos. While the Hubble Space Telescope has revolutionized our understanding of the cosmos over the past 3 decades, the James Webb Space Telescope represents a quantum leap forward in observational capabilities. With its infrared vision, larger mirror, advanced sun shield, focus on the early universe, and enhanced exoplanet studies, James Webb now is rewriting all the textbooks of cosmology.
This kind of data in a fraction of the time that we were before. So I think a lot of the records that we have in the current day universe, those are going to be broken really soon.
Join us as we dig deep into how the latest result of James Webb just broke our universe. Telescopes, such as the James Webb Space Telescope, are a bit like time machines. When they stare across great distances, they are also staring back in time. The link between time and distance in space comes from the fact that light doesn't travel instantaneously. Instead, light in a vacuum travels at a set speed of around 3.0 times 10 to the power of 8 meters per second. But don't worry about remembering that, though. Scientists generally just call it c. That means that anything we look at, no matter how close, is being seen at some point in the past. For objects like the neighbor's cat invading your garden, again, the difference in time between the light leaving and arriving at our eyes is negligible. The travel time of light only really starts making a measurable difference when considering objects in space. Possibly the most natural way of thinking about this is in terms of Earth's most ubiquitous light source, the Sun. The Sun is about 93 million miles, 150 million kilometers, or around 8.33 light minutes from Earth, meaning that we always see the Sun as it was around 8 minutes and 20 seconds in the past. If the Sun suddenly blinked out, Earth wouldn't slip into darkness for around 8 minutes. An observer on Uranus, which is almost 20 times farther away from the star than Earth, wouldn't notice for 2 hours and 40 minutes. This travel time of light becomes really significant when we start to look out into the universe with powerful instruments like the James Webb Space Telescope, Atacama Large Millimeter Array, and the Hubble Space Telescope. The captured light reveals objects as they appeared when they first glimmered, sometimes millions or billions of years ago. As light travels through an expanding cosmos, it's stretched to longer, redder wavelengths. Astronomers can measure the extent of that stretch, called redshift, which can be used to calculate an object's distance. Higher redshifts mean an object is farther away. And for decades, astronomers have been racing to find the highest redshift galaxies, first with the Hubble and Spitzer space telescopes, and now with the Webb telescope. Studying cosmic objects at high redshift is one of Webb's highest priorities. Perched 1 million miles from Earth, the telescope sees in the infrared, which makes it an ideal instrument for detecting longer, redder wavelengths of light. Galaxies spotted by the Supreme Observatory are already forcing astronomers to rethink exactly what constitutes high redshift, or high Z. According to Guido Roberts Borsani of the University of California, Los Angeles, the James Webb Space Telescope has absolutely changed our definition of high Z. In 2015, the most distant galaxies known had redshift values of 8 or 9. But then, the Hubble Space Telescope spotted a galaxy later named GN Z11 around redshift 11 and pushed the first galaxies even further back in time. But now James Webb has eclipsed that, and the redshift frontier has been moved to values of 14, equating to about 13.5 billion years ago. In other words, we are seeing what galaxies looked like at a time when the universe was only less than 300 million years old. The galaxies were first spotted during a deep space survey with Webb's near-infrared camera, one of the telescope's workhorse instruments. Within a patch of southern sky known as the Jade's Origin Field, which is about a quarter of the size of a full moon, scientists found 11 galaxies that seemed to date from when the universe was less than 400 million years old, far more than they had expected. But these galaxies' superlative redshift isn't what makes it so intriguing. In fact, the research team suspects several other candidates awaiting confirmation may have higher redshifts and be from even earlier points in the universe's timeline. Instead, what makes galaxies captured by James Webb so peculiar is its exceptional brightness, size, and color, all of which seem linked to its population of stars. And that, put simply, contradicts the Big Bang, our prevailing theory about the origin and evolution of our universe. According to the theory, most known early galaxies are relatively small and dim compared to modern ones, mostly because their relative youth hasn't afforded them enough time to grow large and laden with stars. But Webb's galaxias seem to be outliers, appearing as especially radiant blobs that suggest it's packing hundreds of millions of times the mass of our sun. Some theories might allude that such brightness comes from a burgeoning supermassive black hole feasting on gas at the center of Webb's impossible giants. But in that case, light is usually concentrated into a much smaller region. Instead, the best explanation scientists have found is that this exceedingly young galaxy has somehow already manufactured about 500 million stars. However, the galaxy's true stellar productivity may be even greater, based on its strange color. Typical growing galaxies produce both high-mass stars, which shine bright and blue for circa 10 million years before dying, and low-mass stars, which shine redder and fainter for hundreds of millions to billions of years. Young galaxies, then, are usually very blue because most of their bright, high-mass stars have yet to burn out. But massive galaxies taken by James Webb aren't very blue. They are actually pretty red. Stardust may have something to do with this. Dust is usually created when stars expel their matter or die. Galactic dust causes light shining through it to appear red. We see this clearly down here on Earth, when dust in our atmosphere turns sunsets red and orange. Another sign that stardust may be the culprit is the galaxy's mid-infrared glow measured by James Webb. Scientists even have found a clue that the most distant object spotted by James Webb, JADES GSZ14, is populated with clouds of ionized oxygen, an element forged in the hearts of stars. However, if dust from dead stars is the explanation, though, it raises a more perplexing question. How could a galaxy so young have already sparked so many stellar generations? Either way, usually gases like oxygen show up only after large groups of stars have lived their lives and died in supernova explosions. So seeing oxygen in a galaxy this young is like if you are an anthropologist and you find an enormous ancient city that has evidence of iPhones. So what then could explain stunning observations made by James Webb? Scientists have developed a remarkable solution. Instead of scratching their head to find a reasonable answer with current knowledge of cosmology and cosmology, physicists and astronomers are starting to get the sense that something may be really wrong. It's not just that some of us believe we might have to rethink the standard model of cosmology. We might also have to change the way we think about some of the most basic features of our universe. A conceptual revolution that would have implications far beyond the world of science. A potent mix of hard-won data and rarefied abstract mathematical physics, the standard model of cosmology is rightfully understood as a triumph of human ingenuity. It has its origins in Edwin Hubble's discovery in the 1920s that the universe was expanding, the first piece of evidence for the Big Bang. Then, in 1964, radio astronomers discovered the so-called cosmic microwave background, the fossil radiation reaching us from shortly after the universe began expanding. That finding told us that the early universe was a hot, dense soup of subatomic particles that has been continually cooling and becoming less dense ever since. Over the past 60 years, cosmology has become ever more precise in its ability to account for the best available data about the universe. But along the way, to gain such a high degree of precision, astrophysicists have had to postulate the existence of components of the universe for which we have no direct evidence. The standard model today holds that normal matter, the the stuff that makes up people and planets and everything else we can see, constitutes only about 4% of the universe. The rest is invisible stuff called dark matter and dark energy, roughly 27% and 68%. Cosmic inflation is an example of yet another exotic adjustment made to the Standard Model. Devised in 1981 to resolve paradoxes arising from an older version of the Big Bang, the theory holds that the early universe expanded exponentially fast for a fraction of a second after the Big Bang. This theory solves certain problems but creates others. Notably, according to most versions of the theory, rather than there being one universe, ours is just one universe in a multiverse, an infinite number of universes, the others of which may be forever unobservable to us, not just in practice, but also in principle. There is nothing inherently fishy about these features of the Standard Model. Scientists often discover good indirect evidence for things that we cannot see, such as the hyperdense singularities inside a black hole. But in the wake of James Webb's confounding data about galaxy formation and the worsening problem with the Hubble constant, you can't be blamed for starting to wonder if the model is out of joint. A familiar narrative about how science works is often trotted out at this point to assuage anxieties. It goes like this. Researchers think they have a successful theory, but new data show it is flawed. Courageously rolling up their sleeves, the scientists go back to their blackboards and come up with new ideas that allow them to improve their theory by better matching the evidence. It's a story of both humility and triumph, and scientists love to tell it. And it may be what happens in this case, too. Perhaps the solution to the problems James Webb is forcing us to confront will require only that cosmologists come up with a new, dark something or other that will allow our picture of the universe to continue to match the best cosmological data. However, there is another possibility. We may be at a point where we need a radical departure from the Standard Model, one that may even require us to change how we think of the elemental components of the universe, possibly even the nature of space and time. After all, having said that Webb's impossible massive early galaxies is posing all kinds of new questions and theories, it's the kind of exciting oddity that researchers were hoping James Webb might reveal. Scientists all agree that James Webb's power has not yet reached its limits. None of them would be surprised if the telescope unveils a new redshift record within the year. In short, thanks to James Webb, we're thrilled to see the extraordinary diversity of galaxies that existed at cosmic dawn, and we're just very excited to see what the community does with these weirdos. What's notable, in addition to unlocking the secret of the cosmic dawn, James Webb now is helping us to lift the veil on how planets form. For a species that grew up on life-giving planet Earth, it's a wonder that we still don't have an end-to-end scientific picture for how planets actually form in this universe. Even with our most advanced observatories, like NASA's Hubble, we've only ever obtained snapshots of stellar systems at a variety of ages and stages. But in very recent years, since the advent of the infrared-sensitive James Webb and the radio capabilities of ALMA combined, that we've been able to piece together a complete picture of these various stages, including what happens and when, with extraordinary implications for our own solar system. Here's the most complete picture we've been able to assemble as of today. It might seem like it's an unlikely story, but every star, as far as we know at any rate, began its life initially as a cloud of gas. Clouds of gas are often both massive and warm, where the kinetic energy of the gas is great enough to counteract the gravitational potential energy binding the gas together, preventing further collapse. However, over time, based on the heavy elements and molecules inside of them, heat gets radiated away, diminishing the kinetic energy of the gas and leading to a star-forming scenario, where the gas cloud undergoes fragmentation and gravitational collapse. Over a relatively short time of a few million years, to perhaps a few 100 million years, Gravitational collapse proceeds in a variety of locations, where the various regions where collapse occurs can contain as little as 1 or 2 solar masses or as much as tens of millions of solar masses. Stars can form in isolation, in small groups, or in clusters with anywhere from hundreds to tens of millions of newborn stars. In each stellar system, that is, where each new star is born, an initially asymmetric clump of matter contracts down to a massive core, where one or more stars will form, surrounded by a two-dimensional disk of material that typically touches and contacts the massive core at the center of it all. One of the paradoxes of star formation is this. In order to gravitationally collapse, gas needs to cool, but in order for nuclear fusion to ignite within a star's core, temperatures need to be remarkably high at 4,000 degrees Kelvin or above. How can you go from a cool, even cold cloud of gas to a dense, collapsed ball of that same material at extreme temperatures? Remarkably, the answer is simple and straightforward from an astrophysics perspective, from gravitational collapse. Remember, in order for a gas cloud to cool, it has to radiate heat away. Radiation that can only propagate away from a region of space through the surface area that encloses it. As gravitational collapse occurs, the volume that the material occupies, as well as the surface area that encloses that volume, both shrink, making it more difficult for that heat to radiate away. As a result, that heat becomes trapped, a consequence of adiabatic contraction. Even though there's nothing driving away the surrounding gaseous matter, the central core of the protostar continues to see its temperature rise and rise, while the density increases as well. Eventually, the core temperature crosses over the critical 4,000 degrees Kelvin threshold, and nuclear fusion ignites, fusing protons and protons together in a chain reaction to trigger the official birth of the star. At last, the star has ignited, and now the radiation and pressure emerging from it increases spectacularly. At the start of this phase, the circumstellar disk is completely attached to the star, meaning that matter continues to accrete onto the protostar, and that the particles and photons emitted by the star are insufficient to stop the continued growth of the star itself. Meanwhile, the disk surrounding the star remains featureless and undifferentiated, hot, swirling, and without any massive perturbations that are detectable even through direct observation with the greatest tools at our disposal. But depending on the particulars of the system in question, this phase will only persist for somewhere between 500,000 and 2 million years. At some point, a protoplanetesimal will grow large and massive enough that it will begin carving features, like a spiral pattern, a gap, or even a ring within the disk itself. Additionally, a gap will first appear between the young star and the disk itself, separating the star from the circumstellar disk that enables the formation of planets, with the interior edge of the gap normally falling well inside the soot line or close enough to the star that even heavy chemical compounds are dissociated by the energy and particles emitted by the star. The emergence of gaps and features within the disk marks the end of the undifferentiated phase. These circumstellar disks, or disks that surround the star, are also known as protoplanetary disks, the locations where planets are formed. Once the star ignites, the material within the disk is caught up in a race against time, as in just a few million years, the majority of the gas within the disk will be blown away from the central star's radiation. This means we have initial imperfections, which seek to grow by gravitational attraction, drawing on matter from within their orbit, as well as exterior and interior orbits, to produce protoplanets and eventually full-fledged planets, while surviving gravitational encounters with the other objects that are racing to do the same. For as long as the gaseous matter persists in great abundance where it is. In the chaos of these early environments, many interactions will occur. Small protoplanetesimals will collide, sometimes binding together to form larger protoplanets. sometimes smashing into one another and blasting their bound material apart. Young planets and protoplanets will gravitationally interact, where they can combine, be ejected, collide, or get hurled into the central star. The largest initial planets gobble up the material around them, becoming the largest worlds in their stellar systems, and the migration of planets perturbs the orbit of everything nearby, often destroying these lower mass worlds and preventing them from becoming surviving planets. And yet, despite this initial chaos, once enough time goes by, a more stable-looking system emerges. After approximately 10 million years have gone by, the gas-to-planet mass ratio will have dropped substantially, from an initial ratio of around 100 to 1 or greater down to a more modest 1 to 1, indicating that the planets within this stellar system have now largely taken shape. In our own solar system, we typically assume that the 4 gas giant planets we know today, Jupiter, Saturn, Uranus, and Neptune, as well as possibly 1 or more additional large planets, all formed during this very early phase, with Jupiter initially being much closer to the Sun than it is today. Whatever the initial planetary configuration was in the inner solar system, it was likely destroyed, absorbed, ejected, or hurled into the Sun by Jupiter. But even with relatively low amounts of gas remaining, the outward migration of Jupiter paved the way for smaller bodies to form and survive within the inner solar system. Bodies such as the ones that would become the modern-day Mercury, Venus, Earth, and Mars. That's because planet formation doesn't end abruptly or all at once, but simply transitions to a different stage once the gas has mostly disappeared. Once the free gas from the initial disk that surrounded the newly formed star has almost completely blown away, planet formation is over, right? That naive picture was, in many ways, the leading idea in planet formation for several decades, so if this is what you thought too, know that you weren't alone. In fact, this is probably true for the majority of large, massive planets that formed in the universe. Instead, we now know that the material that remains in a young planetary system includes some gas, young planets, and planetesimals at a variety of distances from the star, an enormous number of solid bodies at various frost lines, or when different compounds transition from solid to ice or vice versa, and a great number of solid bodies in the outer system, at Kuiper Belt-like distances and beyond. This stage in the evolution of stellar systems represents a time of heavy bombardment of planetary bodies by comet-like and asteroid-like bodies, as well as a time where there's great potential for giant collisions. If you grew up in the late 20th or early 21st centuries, you probably learned about a time in our own solar system's history known as the Late Heavy Bombardment, which lasted until about 700 million years after the formation of the Sun and planets. Evidence for this period exists across the ancient surfaces of many well-known bodies, from the Moon to Mercury to Mars and more. However, it's kind of a misnomer in a sense. Nothing happened that was all that special to increase the bombardment rate that late in the game. Instead, there was a massive bombardment period that persisted for the entirety of the first 700 million years of our solar system's history. And it's more like the extreme violence ceased about 3.8 billion years ago, right around the time that the first smoking gun evidence for life on Earth appears in the fossil record. Many violent events occurred during this bombardment period. About 50 million years after the circumstellar disk phase ended, a giant collision between young Earth and the protoplanet Theia occurred, giving rise to our moon. Mars experienced a giant impact, giving rise to Phobos, Deimos, and a now destroyed massive third moon that fell back onto Mars. Pluto received a great impact, creating its system of 5 moons. Triton, once the largest and most massive body in the Kuiper Belt, migrated inward and became gravitationally captured by Neptune. Only after all of these events occurred did bombardment end, signaling the end of the debris disk phase of our solar system's history. Just as humans go through a variety of phases as we grow up, from infancy to toddlerhood to childhood and adolescence to adulthood, so, it appears, do stellar and planetary systems. During the protostar and undifferentiated circumstellar disk phase, planets are not yet conceived. The seeds for them are destroyed just as easily as they are created. As the circumstellar disk begins to differentiate, and it is not yet known whether the earliest differentiations that occur lead to planets or get completely destroyed, planetesimals, or the seeds of planets, get created. They grow rapidly, like a gestating human fetus in the womb. During this phase, planetary miscarriages are common, getting devoured by other, larger baby planets, getting ejected, or even getting hurled into the parent star. Then, when the circumstellar disk phase gives way to the debris disk phase, these baby planets start to grow up, going through a long childhood and adolescence, experiencing many violent episodes where moons around rocky planets are primarily formed, and where a few lucky, tiny, leftover planetesimals can persist as full-fledged planets, much the way Mercury and Mars likely did. And then, finally, when the debris completely clears out, which can occur quickly, within a couple of 100 million years, or which can take a long time, nearly 1 billion years, the planets that are left are fully mature, with only the rare gravitational interaction upsetting the orbits of the planets over the subsequent billions of years. There are still a great many details that need to be investigated about how planetary systems form and grow up, but at this point in time, in mid-2024, we have now assembled a more comprehensive and detail-rich picture about the formation of planets than ever before. Yes, very high mass and very low mass stellar systems are likely to deviate from this standard story, and there's likely to be a lot of variation among individual systems even within this story, just as there are always going to be a few extremely tall, or short, or heavy, or light humans within a large enough population at any given stage of development. However, for the first time, we can assemble a detail-rich story of planetary evolution that's driven by a wealth of data that was unavailable to astronomers prior to observatories like ALMA and James Webb. The story, quite simply, is one of the evolution of matter from a uniform, undifferentiated disk around a protostar to one that's virtually gas-free, that simply contains mature planets and planetary systems orbiting around one or more stars in a stable fashion. The transition from a circumstellar disk phase to a debris disk phase, as well as the persistence of a debris disk over long periods of time, remains poorly understood, and it's hoped that future observations of these young systems will help us fill in the gaps we presently have. Nevertheless, we have a compelling story for planet formation across the universe that is, at last, consistent with our own solar system's history. Now that we have an outline for how planets and planetary systems form and evolve, it's time to find out just how rich the tapestry of existence can truly be. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.